Hello, everyone, and welcome to the second video on the standard normal distribution. In the first video, we did a very quick recap on the properties of the normal distribution and the empirical rule. So in this second video, what we're going to talk about is how to apply the empirical rule, and we will try to make use of these examples to introduce a concept of the standard normal distribution and why it is in fact necessary. So we begin with this example, wherein the situation that we're going to work with presents that a certain batch of students took the same 35-point math exam, and their scores happen to be normally distributed with a mean of 19.9 and a standard deviation of 4.7. Now, Anna, one of the students who took the test, um, scored a certain value that places her in the middle 68% of the batch. The question that we need to answer is what is likely Anna's score? Now, since we know that the distribution is normal, that means that the empirical rule should apply to this distribution, which means that if Anna's score puts her in the middle 68% of the batch, that her score is should be found between -1 and +1 standard deviation. But before we take a look at what exactly those scores are, we will make use of the mean and the standard deviation to apply or to identify certain values along the x-axis. At the middlemost part, right about the peak of the distribution is where we would find the value 19.9, which is not only the mean, it's also the median and the mode. And to the right of it are integral multiples of we make use of integral multiples of the standard deviation to add to the mean, which is 19.9. So we have 19.9 plus one standard deviation, that's 4.7. So we get 24.6. Then we add another 4.7, that's 29.3, and another standard deviation, that's 34. Going to the left, we subtract the same value, the standard deviation of 4.7. So 19.9 minus 4.7 would give us 15.2. And then minus another 4.7, you get 10.5. And finally, three standard deviations to the left of the mean would give us a value of 5. All right. So going back to the question, we are asked to find what are the possible values for Anna's score. We cannot actually determine what exactly is Anna's score in the test. But since we know that it should be in the middle 68%, and we also know that the middle 68% in a normal distribution is bounded by the +1 and -1 sigma or standard deviation about the mean, then these values should correspond to anywhere between 15.2 and 24.6. Therefore, the simple answer to this question is Anna's score in the test must be some value between 15.2 to 24.6 because these values cover the middle 68% of the batch. All right, let's proceed with question number 2. Dexter is another student who took the test, but he scored 29.3 in the exam. So that's 29.3 out of the 35. What percent of the batch scored lower than he did? Let's answer this question first before we proceed with the second one. We're dealing with the same distribution, so we're going to make use of the same representation of the normal distribution that we presented in the previous slide. But this time, what I want us to do is to identify or locate where Dexter's score is along the x-axis. So Dexter's score of 29.3 places him exactly at 2 sigma or 2 standard deviations away from the mean. It conveniently, let me use the modifier conveniently, places Dexter at exactly 2 standard deviations away from the mean. And it's convenient because we will actually be able to make use of the empirical rule to answer the question of what percent of the batch scored lower. So since what we are after is identifying the percentage of the batch who scored lower than Dexter, who scored is 29.3, using his position, the position of his score along the x-axis, we're actually after the area that is covered by the region to the left of 29.3. And that's the shaded region that we see over here in purple. We need to identify or we need to determine what that area is by making use of the empirical. Now, knowing that from the leftmost tail of the distribution, or the left tail of the distribution up to the mean, that's already 50%. And from the mean to two standard deviations, that's half of 95, which is 47.5%. We can simply add 50 and 47.5 to find that the area of this region is 97.5%. So we say, as a response to the question, that by the empirical rule, Dexter's score is greater than 97.5% of the students in his batch who took the same test. So notice that even if 29.3 is not really that high of a score, if we consider the mean and the standard deviation, Dexter's score is actually quite excellent when you compare it with the rest of the students in his batch, because it places him at 97.5%. That and there's only quite a few of the students in the same batch who scored higher than he did. And that's the next question that we are asked. So how likely is it for a randomly chosen student to score greater than Dexter? So the answer to this question is quite simple, but it's phrased differently from the previous one. If you notice, um, this emphasizes that the area under the normal curve can serve different purpose. It can be used to identify the proportion of individuals within a certain distribution that fall within certain scores, and that's what we did with the first part of this item. But the second item is asking us not of proportion or percentage, but it's asking us about probability. And that's the idea is how likely, or how what is the probability that when we randomly choose someone from the batch, what how likely is it that that student scored higher than that student? And because only 2.5% of the batch was able to score a greater or scored better than Dexter, then that means that that probability is also 2.5% or 0.025. That 0.025 or 2.5% is represented by the region. It's the area of the region to the right of Dexter's score of 29 points. All right. Let's consider another example. So this time, we have another student who took the same test. Jasper, on the other hand, scored 25.5 in the exam. So what percent of the batch scored lower than Jasper? Okay. So if we consider Jasper's score is between one standard deviation and two standard deviation away from the mean. 25.5 is between 24.6 and 29.3. So if we estimate that using our x-axis here, it's probably somewhere in that position. Um, the one that's represented or pointed out by the purple vertical line. But the problem now is, if we cannot base, or we cannot find the answer by just basing it on what we know from the empirical rule. So something that this problem should help us realize is, we know that we are after, or we want to identify the percentage or the probability that x is less than 25.5. We know that's what we want to find or look for. But while the empirical rule is very useful in approximating some region under the normal curve, the problem is it is limited to regions bounded by integral multiples of sigma, or the standard deviation. So the empirical rule is very helpful, but it can only do so much when we are asked to solve with problems that the boundaries of the regions that we work with are conveniently placed on integral multiples of the standard deviation. But in this case, we notice that the position of the score that bounds the curve, or the region that we are after, is not in either one or two standard deviation. It's actually somewhere in between those. So the question now is, how do we find answers, or how do we solve questions such as these? And this is where the idea of standard normal distributions come in. But before we talk about that, I think it's necessary that we point out another reason why there's a need for us to, as what we call it, standardize scores. And that's something that I would discuss in the next video.